Hi, my name is Santiago García Medina. I am a student of La Libertadores University, and in this video I am going to present you the exercise 11 104 of the book. And the statement says the following. A commercial airplane has a total mass of 150,000 pounds and a wing platform area of 1,800 square feet. The plane has a cruising speed of 550 miles per hour and a cruising altitude of 38,000 feet, where the air density is 0.0208 pound-cubic feet. The plane has a double-slouted flaps for use during takeoff and landing, but it cruises with all flaps retracted, assuming the lift and drag characteristics of wings can be approximated by NACA 23012. Determine A. The minimum safe speed of takeoff and landing with and without extending the flaps. B. The angle of attack to cruise steadily at the decreasing altitude. And C. The power that needs to be supplied to provide enough thrust to overcome drag. Take the air density on the ground to be 0.075 pound-cubic. We are not going to consider the drag and the support by other parts of the plane other than the wings, and we are going to solve the exercise with data and formulas from the Cengel Fluids Mechanics book. We calculate W multiplying the mass by gravity, obtaining 4,830,000 pound force, and we are going to pass the speed to its dimensional units that are feet per second, obtaining 806.6 feet per second. At point A, they ask us for the minimum speeds corresponding to the loss of lift conditions without and with flaps respectively. Well, we are going to use formula 1124 of the book for this. We have W and the area, but we lack CL, which is the maximum coefficient of lift. For this, we will go to graph 1145 to find CL max 1 and 2 respectively. Now that we have all the data, when you replace and see the minimum speed 1 is 214.87 feet per second, and the minimum speed 2 is 143.39 feet per second. Then the minimum safe speeds to avoid the loss of lift region are obtaining by multiplying the previous values by 1.2. We see that the minimum speed 1 without flaps is 257.8 feet per second, or 175.8 miles per hour. At the minimum speed of flapping is 172 feet per second, or 117.3 miles per hour. Now we are going to solve the point B, where we are asked for the angle of attack to fly stationary at cruising altitude. For example, when an airplane flies stationary at a constant altitude, the lift must be equal to the weight of aircraft, FL equals W. Then the lift coefficient is determined by replacing in the formula. We use equation 11/6. We replace and we get the CL, which is 3962. With this, we look at the graph to determine the angle at it gives us an approximated value of 3.3 degrees. Next, point C. At this point, they ask us the power that needs to be supplied to offer enough thrust and overcome wind drag. We have to go back to the charts and find the CD to replace in the formula. The CD value is approximately 0.016. Now we only replace the values we have in the formula. Our results gives us 60,052.72 pound force. This is the drag force extended on the wings. To determine the power, we multiply the thrust by the speed, obtaining as a result of 6,613.75 kilowatts. Okay, thanks for your attention.